How's everybody doing today? Welcome back to the Math for Healthcare video lecture series. And here we're digging a little bit further into exponential functions, and we're going to start looking at continuous compounding. So far we've looked at periodic compounding. So what am I saying with that? Well, first of all, remind ourselves, periodic compounding is what we've seen so far. Okay, and this slide that I have up here, this is we looked at last time. And growth, we get the exponential growth or decay, and in general, it's equal to the function, it's equal to the initial amount, P naught, times 1 plus R, where R is the percent change per compounding period, raised to the KT, where K is the number of compounding units per unit of time. And T is, of course, your time in your chosen unit. Okay, and we looked at a few of those. It was one way to think about it, but remember, in all those cases, 1 plus R equals some number, whatever, call it A, right? We saw, if R equals 0.2, then A is equal to 1.2, and what does our equation look like? Let's say we start with one thing. We got 1.2 raised, and let's say it's every minute, so raised to the t, and we looked at something like that. And this is another way to think about general exponential functions. This a here, which we call the base, in this case is 1.2. That's we have this on this other slide. Another way to write that, and remember, a is just the parentheses 1 plus r. Right? Our function of x looks like this. Again, p naught is still our initial value because a raised to the 0, no matter what a is 1. And if a is greater than 1, there's exponential growth. If a is strictly between 0 and 1, it's exponential decay. And we can look at two examples of those, the graphs of y equal to 2 to the x and y equal to 1/2 the x. Notice for y equal to 2 to the x, that's I put in my Desmo screen there as f of x, and it goes through the y-axis at 0, 1. Both do, right? That's the initial point. P naught is 1 is what I'm saying for each of these. But notice the difference. In red, we have the graph of y equal 2 to the x, which we have seen a few times there, and it is increasing because there a is greater than 1 and we have exponential growth. Now y equal to 1/2 x is a is between 0 and 1, so that it's decreasing, and we have exponential decay. And I'd say you should open up Desmos and play around, look at a couple different exponential functions. Play is an important part of learning about things and understanding them, right? One thing I want to mention here before we move on to the continuous compounding is that here y equal to 1/2 raised to the x is equal to, same thing as 2 to the negative x, since 1/2, 1/2 to the negative 1 equals 2. All right. That's just kind of a reminder of some things we did in a review, and to recognize that they're the same thing. You just may see it sometimes as 2 to the negative x. Okay, so went too far. Now here I crossed some things out. Basically, I just want to do the growth rate and decay rate to match with my previous slide and have that be r. So if a quantity y grows or decays continuously as a function of x, then the relationship can be modeled with this base e, where e is approximately 2.71 blah blah blah. It goes on forever. It's much like pi. It's a very special number. We call it's Euler's number. If you don't know Euler, Leonard Euler is a very famous, proliferate mathematician. Did amazing things for humankind in what he discovered. But anyway, that's a special number. So that means that, by the way, the basic function, let me go in here. So if I plug in e to the x, right? E to the x. Yeah, it makes sense. It's a little above the graph for f of x equal to 2 because it's bigger than that. And it should be pretty close to y equal 3 to the x because it's about 2.71. Now that number is very special. And for technical reasons, we put a lot of exponential in front in terms of that e, as e is the base, and specifically it's the continua. It's the way we write a continuously exponential growth or decay. Right? So r is the continuous growth rate if r is greater than 0, and it's the continuous decay rate if r is less than 0. And I do want to note that if you do not know how a particular quantity compounds, you can assume it compounds continuously, which seems a little funny, but it turns out that it's a natural number to use there, and most of the time that's how we model things, and that's how you'll see things in papers or in books and such. All right, so let's just look at an example real quick. All right. Let's say, suppose we have 10 bacteria. And by the way, continuous it makes sense for populations, right? Because generally populations are continuously compounding. When you think about a birth rate, there's no specific set time everyone's having children, right? It's continuously happening. So we have 10 bacteria. That grow. No, I should say we have a population of 10 bacteria that grow by 20% continuously. Okay, and I think you guys are going to like this one. It's almost, it's a little bit more canonical. What's our function here for the number of bacteria? Let's say t is in hours, right? This is going to be, well, we have the initial condition, or initial amount of 10 there, and then e, that was raised to the r is 0.2 t. Okay, and if we want to see that over here, I'm going to get rid of some other things. And what would that growth look like? As we expect, it goes through 10 and has this exponential growth. And it's continuously growing at 20%. Okay. So for continuous compounding, we use this formula here, the initial amount times e to the rx, where r is the continuous growth rate or decay rate. Okay, so let's look at another example. It turns out that in bank accounts, they grow like populations, all right? And here, well, let's say suppose a bank account compounds continuously at 3% annually. If you deposit $2,500 into the account, how much will be in the account in 3 years? I want to point out the compounding is continuously. Annually just means we want our t to be in years. T in years. All right. And what we want to do is want our function. Again, we go back, look at our formula basically. Our initial amount is 2500. Since it's continuously, we have a base E, and then 3% is 0.03 t. Okay. So just to give you an idea of what that looks like, I put in 25 because I didn't want to re-scroll my screen up there. It's just in hundreds of dollars then, right? That's what the function h of x on down your lower left in Desmos there looks like. And if you want to look long term, you see it grows real good. It grows real nice. And that's how we do that. And so let's say we want to know, okay, so let's suppose we have this account, right? How much money is going to be in there at, let's say, f of after 10 years. We know how to evaluate a function by hand. This is e times e raised to the 0.03 times, and we substitute 10 in for our t. But of course, we just use Desmos so we don't make a little silly error. And that says, on Desmos it says 33.74, but because we're in hundreds of dollars, after 10 years you'd have $3,374.65 or so. Right? And again, I'd go ahead and play with that. Now, we got our question. How about in 3 years, how much is going to? So there we plug in 3. And it looks like that's going to be $2,735.44 about after 3 years in your account. So an interest of what? $235-ish or something like that. That's what you'd gain over. Again, that's over 3 years. And write that here. 3 years, 500 e to the 0.03 times 3, and that came out to be approximately $2,735.44 ish. Okay. All right. Well, however, we may be asked. Now we got the same account, so I'm going to rewrite my function f of t equal to 2500 e to the 0.03 t. And again, that's what I have graphed here. It's just in hundreds of dollars rather than in dollars. We want to know how long it will take for balance to get to 10,000. Well, we could scroll out and get a little idea. Okay, 10,000 would be 100, right? So it looks like somewhere around, where is that? 100, about, looks like maybe 50 years-ish. But what are we really, let's think about that. What are we asking? How long it will take? We want to find a t value so that our function comes out to be 10,000. All right? And we know 10,000 is equal to 2,500 e to the 0.03 t. Okay? Okay, so maybe we say, it seems reasonable. The first thing, we may want to divide both sides by 2,500. Better check on. Which is 4. So we're dividing both sides by 2,500, and we get 4 equals e to the 0.03 t. Okay. We're kind of stuck there. Right? The issue is we have the variable up in the exponent. We don't know yet how to get that out of there. There's a couple ways, and this is going to be the next video we'll talk about it, but one of the main ways is using logarithmic functions. So we're going to have to meet those first, and then we'll start solving these. But I do want to say is notice you're using technology, you know, hope is not all lost. What did I say, somewhere about 50? Let's see, age of 50. And that, remember, I did it so really just to make sure times 100. There it is. That's 11,000. So somewhere around 50 years or something, maybe more like 45-ish or something. Close. 47. So you could play around with things like that, and we could get close, but we'd like to be able to solve it and understand those. Plus, the nice thing is logarithmic functions are going to give us some nice applications in nursing, mainly the pH, measuring pH, and also for decibels as far as understanding hearing tests and those sorts of things. All right, hope you enjoyed this video, and next time we'll learn how to solve, well, we'll meet the logarithmic function. All right, have a great day.